Okay, now we look at this slides which talks about different types or different classification for gas liquid separators based on mechanical separation. You can have gas liquid separators, gas solid separators, liquid liquid separators, solid liquid separators. In this chapter we will be mainly interested to talk about the gas liquid separators. So normally we will be looking at this zone specifically to look at. And now in the next slide we'll talk about the principle of separation being physical, mechanical or momentum, and we'll explain what is the main concept or what's the driving force, what's the main concept behind or the mechanism for that separation. Okay, now we are talking about the separation principle or the main mechanism for the separation in gas liquid separators, which are mainly three mechanisms: filtration, gravity and momentum. Filtration is simply done by simply applying porous media or porous barrier against the flow of the fluids, and based on the size exclusion or due to the presence of porous, the separation will take place. And this is very similar or very common or very similar to what you have done في اللابوراتوريز عندكم اللي هو ممكن تكون استعملت الفلتر paper to separate liquid from gas, liquid from solid. The second one is separation by gravity, which is again is very similar to what we have explained اللي هو physical separation اللي هو بيعتمد على السايز تاعت الدروبلت. If you have size large droplet size, this means that the gravitational force عليها حتكون أعلى من drag force, and as a result it will settle down. And the last one is the momentum separation. In the momentum separation what we are referring to اللي هو separation based على density تاعت الفلويد. So if you have two fluids flowing in the same direction and both of them and each one has different density than the other one, the heavier one, if you apply resistance to that flow, what will happen? The heavier one will move slower than the lighter one, or the one that has lower density will flow faster than the lower that has high density, and as a result the separation will take place between these two fluids due to the change in the momentum as a result of change or difference in the density. Okay, now in this slide we'll explain what are the major section or what are the major component of any vertical gas liquid separator. First of all, let's look at the sketch or the scheme at the left side of the slide, which shows you the dimension for common industrial vertical gas liquid separator. This will give you an idea about how much, for example, should be the height of the inlet diverter, how much should be the sludge capacity section, how much should be the demister thickness, and all other specification from industrial point of view. But this doesn't mean that these numbers are fixed for our separator. No, it depends on the flow rate, it depends on the characteristics of the fluid that you are dealing with. But now let's look at the right side, the sketch. This sketch shows the major component or the major section that has to be inside any separators, where you can find that you have the first component is what we call the inlet inverter, and we have also something called the mist extractor, and as a result you can see that once the gas flow in, the main duty of the inlet diverter is to cause what we call the change in the direction of the flow, and as a result liquid flow at the bottom and the gas will flow up. So the main duty of the inlet diverter or the inlet baffle is to change the direction of the flow. So the liquid will flow down and gas will flow up. And if this gas stream has very tiny liquid droplet, what will happen? It will start to be collected at the demister, and then it will settle down, and then you will produce what we call the gas stream that's free of liquids. We have also something called gas gravity section that we'll explain also later, and we have also the liquid gravity section as well. So these are the main characteristics, or these are the main section for what we call vertical gas liquid separators. Most important thing is to understand is that the inlet separator or the primary separation took place at the inlet diverter or the inlet separators, where the fluid that contains gas and liquid will hit the inlet diverter, and as a result the direction of the flow will be changed. The liquid will drop down, the gas will flow up, and then the gas, if it has tiny particle or tiny liquid droplet, will start to collect at the mist extractor or the mist separator. And again here we emphasize on the fact that you will need two-phase separator if you are separating water from gas, and you will need three-phase separator if you are separating gas from oil and water. And the three-phase separator, you will need to install what we call the water draw-off boot that will be installed at the bottom of the separator. And as we mentioned earlier, you will need the inlet buffle or the inlet diverter at the gas inlet, and the mist extractor will be needed only if you are dealing with gas stream that has very tiny water droplet. You will also need what we call the vortex breaker in order to prevent the formation of vortex. And finally, as we explained several times, that these separators can be configured as vertical, horizontal, or spherical. Okay, this slide is just an explanation of what we have already explained, but I'm gonna just refer to it or repeat it narratively. So here we're gonna talk about the primary separation section, which is the result, or which is caused by what we call the diverter buffle, or what we call the inlet diverter. So what will happen, the gas stream carrying the liquid will hit or will strike the inlet diverter. This will cause what we call the primary separation due to the change in the flow or the direction. The gas leaving the top and the liquid will settle at the bottom. The gas leaving from the top, if it has very tiny water droplet molecule, okay, what will happen? Then you will need to use what we call the mist extractor, and the mist extractor will start to collect all these tiny molecules, make them large, and then separate them. Okay. Normally there will be change or sudden change in liquid volume flowing inside the separator, and this can be controlled by adjusting the height of the separator. Okay, mixed extractor will not be always used. Sometimes you will not need to use the mixed extractor at all. You will need to use them if you have very tiny water droplet. Vertical separators are bigger and more expensive, but they're normally used when you have gas to liquid ratio or high gas to liquid ratio, or total gas volume are very small. Now let's talk a little bit about what we call the horizontal gas liquid separator. So we talked about the vertical gas separator. Now we'll talk about the horizontal separator. The main section in the horizontal separator and the vertical separator are the same. The only difference that the separation take place in the vertical direction in the case of the vertical separator, and in the horizontal separator take place in the horizontal direction. So the horizontal separators are very efficient when you have large volume of total fluids, which means gas and liquid, or when you have high liquid to gas ratio. It's better to use what we call the horizontal separators. They have the advantage of providing larger surface area for the gas separation, and therefore it will be better to use them. And similar to the concept of the vertical one, once the gas and liquid enter the separator, it will hit or it will strike what we call the inlet buffle or the inlet diverter. The vapor and liquid will flow along the horizontal direction of the separators, and not all the cross section will be occupied by any of the fluids, being liquid or the gas. It will be distributed. We'll see this in the scheme next on the sketch, next slide. Okay, now let's look at this slide or this sketch. This sketch gives you an idea about horizontal gas separator. We're going to use this sketch to give an example of how can we separate a three-phase flow. Here we have an example where you have gas stream, hydrocarbons, and you have glycol streams. And if you can see, we have very similar component as the vertical horizontal. You have the inlet, the buffer or diverter, and you have the mist here. So what will happen here, that the gas stream coming in carrying gas hydrocarbons and glycol will strike the buffer, the inlet buffer or the inlet diverter, and as a result the flow of the stream will be as following. This is the flow of the liquid stream, and this is the flow of the gas stream. All of them, both of them will continue to flow in the horizontal direction because this is the direction of the separation, gas or liquid. Gas will go to the demister in case we know that there are very tiny water droplets. It will go through the demister. Otherwise, it will go straight forward to the outlet, and it will give me what we call the gas stream free of liquid. Now let's look at the liquid. Now the liquid stream has mainly two components, has the hydrocarbons and has the glycol as well. So I have two material, they are in the liquid phase and they have different density, which means that they will continue to flow this way, but these two material has to be separated. So the heavier material will be separated at the bottom. Sorry, this is the hydrocarbon here, and this is, let me just grab the eraser. Okay. And here will be the glycol. So the glycol, which is the heavier liquid stream, will be separated through the put, because it's the heavier material, it will settle at the bottom of the separator. And the hydrocarbon, which is lighter than the glycol, will flow in the top of the glycol, and it will be separated through another outlet, which is the liquid hydrocarbon outlet. And as you can see here, we have something called overflow buffle, and the main duty of this overflow buffle is to separate the glycol, which is in the boot, from the hydrocarbon, which is going out of this exit. So this example illustrates how three-phase horizontal gas liquid separator can work or can function. Hopefully it's little bit this animation, this information is a little bit helpful for you to understand how it will work or how it will function. But as you can see, you still have the major component that you can see in the vertical separators, which is the inlet buffle and the mist extractor. And you have to keep in mind that in the inlet buffle you have always what we call the primary separation. And this sketch shows the dimension and the design for the last configuration, which is the spherical gas liquid separator. And normally these separators will be used for high pressure service, and they are, in fact, they are not very common in the industry, but you can find them in some industry, but they're not very common, similar to the vertical and horizontal separators. Now let's look at this slide. Let's go in more details. How can I split, or how can I describe any separator? So any separator, any gas liquid separator, being vertical, horizontal, two-phase, three-phase, will have the major four sections. You have first what we call the primary separation. The second will be the gravity settling, and the third will be coalescence. So coalescing, and the third one will be the liquid collecting section. So these are the major four sections that can be found in any gas liquid separator. And the next slide I will show it to you in the sketch in the Now in this slide we're going to learn how to lay out the primary section, or the gravity settling section, or the coalescing section, or the liquid collecting section, which are the four major sections, or the four major separating section or categories in any separator, on classical vertical or horizontal separator. Now if you look at the one, or the shape or the scheme at your right hand side, which is for the vertical separator. Okay. So now for the vertical separator, you can see that we have section A, which is in fact the gas
liquid separator section, or what we call, so let me put it this way. So this here you have flow of the feed, which has gas and liquid coming into a vertical separator. So we have 4 separation area: area A, area B, area C, and area D. Okay, so let's look at them one by one. So now area D will represent what we call the liquid collecting region, where you're gonna start to collect the separated liquid from the gas stream. And then if you are dealing with 3-phase, then this means that you will improve, or you will integrate some other methods such as the POOT in order to separate the 2 liquid phases from each other based on their density, as we have seen before. So this is what we call the liquid collecting area. Now if you go to the second one, or the C, which is the this section, which is the mesh or the demister, this is represent what we call the coalescence section, which will be dealing with the very tiny particles, and these very tiny liquid particles will start to accumulate and aggregate on the mesh wires, and as a result their size will grow up, and then they will be heavier, and then they will separate from the gas stream. And this means that you will not always have the demister, but the demister will be perfectly used in case you have what we call the very tiny liquid particle entrapped in the gas stream. Now for section B, which is in fact the let me just grab the color. For section B, which is in fact the gravity settling section, in this section you will try to separate in fact liquid that's already separated from the gas stream in section B. And section A, which is the primary separation, which is the, as we mentioned, which is the inlet buffle. And this the main target of the inlet buffle, that I'm gonna just draw it right now in red, let me put it this way, that the gas, when it enters, it will hit the buffle, and as a result the liquid will go down and the gas will start to go up. So this is the main section, or the main duty for the inlet buffle, or the primary separation. So you have the primary separation, you have the gravity settling, you have the coalescence or the demister, and you have the liquid collecting. Now let's go to the second one that's at the left side of the screen, or the slide. You can also see that you have the inlet buffle, or the inlet separator, which represent the primary separation. And then you have the P, which is go horizontally this way. In the vertical one, it goes vertically. The separation goes vertically. In this configuration, the horizontal one, part P or section P, which is the gravity settling, is going horizontally. So as you move from, let's say, from this point to this point, you achieve more separation. And then you get also part C, which is the section C, which is the demister that deal with the very tiny particle. And the last one will be section D, which represent the liquid collecting point, which can also include the POOT in case you are dealing with a 3-phase separator, or you deal with 2 different liquid that has 2 different density. So this is a good demonstration or representation of how we can lay out the 4 main separation section in any vertical or horizontal separator.
So now we know exactly how or what are the main section in any separator. So now any separator, in order to operate sufficiently or efficiently, it must fulfill the following requirements. First of all, it must have what we call the primary section to remove the bulk of the liquid droplet from the gas stream. And then it should have sufficient liquid capacity to handle the changes in volumetric flow rate of the gas and liquid. And the third one, it must have sufficient length or height. And why is that? In order to allow more height or more length for the liquid droplet to settle by gravity. And fourth one, it should have what we call the vortex breaker, or somehow to reduce the turbulence. Why? Some means to reduce the turbulence. Why is that? Because at the end of the day, in the major separation mechanism in the gravity section is by gravity, which means that we will have to wait for this material to settle and separate by gravity, which means that we should avoid having turbulence in that section. So we need to reduce the turbulence as much as possible, and then you might need or you might not need the mist extractor or the demister, proper back pressure and liquid level controller to control the liquid level inside the separator. So these are the main requirement to operate, or in any separators to operate it efficiently. Okay, now normally for the design in oil and gas industry, normally you will be looking at liquid or gas liquid separator that will handle or deal with water droplet around 150 micrometer. So the common sense or the common practice that if your liquid droplet is around 150 micrometer and up, then the gravity settling will be good enough to remove this water droplet or liquid droplet. If your liquid droplet is less than 150 micrometer, this means that you will need to install what we call the demister or the mesh to reduce or to improve the efficiency of the removal. And this demister or mist again will collect this tiny water droplet which is less than 150 micrometer and will collect them and separate them. How it works? Typical values that if you have, for example, 100 millimeter thick wire mesh demister, 30 to 40% of the droplets that's greater than 20 micrometer will pass through that demister. But if the water droplet is between 60 to 70 micrometer, the same mesh or the same demister will collect 100% of this water droplet, and the separation will goes up to 100%. So as you can see, the efficiency of the separator, the efficiency of the primary separation, the demister, everything is dependent on the size of the droplet.
Now this slide gives you an idea about how the horizontal, for example, separator looks like in real life, how it looks like in the industry. This is like horizontal separator, and this is the scheme, or this is the mechanical design or the mechanical drawing of this horizontal separator. And this is what you are seeing here on the left side is what we call the mesh or the demister. So the demister, the mesh, the mist extractor are all the same, so you can refer to it as mesh, demister, or as what we call the mist extractor. Those are all the same, and they are all based on the fact that they're gonna contribute, or the wire that's available in the mesh or the mist extractor or the mesh, they are working toward what we call the aggregation of the small or the tiny water droplet to form what we call the large droplet. And as a result, once the large droplet formed, their size become large and their weight become large, and as a result it's easy to be separated from the gas stream. And we're going to see later on more details how the mesh extractor or mist extractor or the mesh or the demister work.